In this video I want to tell something about elaborating and working with a certain chip. Especially about long wiring, short wiring, when you want to do, say, serious experiments with all kinds of electronics, and in this case it is this chip. I bought it, it's approximately €1 or so, and here is that more information. I wanted to make a Squarewave oscillator with it, but this chip is not only a voltage controlled oscillator, but also a phase locked loop. And I have to say, I don't know anything about phase locked loop circuits, so don't ask me anything about it, but perhaps it's interesting to show what I've done up until now with that chip. It's just, like I thought, also a Squarewave oscillator, and it gives out very, very pure square waves. Not comparable to, say, other circuits that I've made in the past with, say, dielectric transistors or simple A-stable multivibrators. This is a very interesting and properly working chip that surely can work, and then I mean without very critical wiring in the proper frequency bands. I hoped that when I say clicked here, I got more or less good overview. But anyway, I see here, for instance, something anyway. This is about that chip. High-speed silicon gate, CMOS devices, pin compatible, etc., etc. And as far as I could see, the chip was originally manufactured in the 1970s. Anyway, so this is no good information. Sorry that I clicked here. Everywhere on the World Wide Web we have kinds of sources that can inform us about the data sheets, but the best website is alldatasheet.com. Here we have a lot of say advertisements. I don't need it at all. So let's go to the circuit, how it is in real, and of course has everything to do with the fact that the data sheet was not showed directly and immediately on the World Wide Web, so that I could talk more about it, tell more about it anyway. This is, by the way, the circuit, how it is made. I only can show now the practical circuit. The chip is here. It needs 5 volts, maximum 5.5 volts. It's served via a 7805 regulator. That regulator goes to a transistor here. That transistor drops down the voltage from, say, 40 volts. That is generated here, 40 volts, to approximately 12 volts, and then it is dropped down to 5 volts, and that is the 5 volts that the chip needs to work. I have on purpose used very small main transformer. It can only give out, say, 50 milliampere or so. I hope that it will that will not hinder my further experiments with this circuit. Anyway, again, here is that chip. This is pin 1, and here we have pin, say, the supply pin here approximately. Let's see what this circuit can bring, and then especially I want to talk about, say, changing an experimental circuit into a more or less not experimental circuit, etc. You can see here directly that all these wires are very long here. And for instance here, this resistor, this was all, say, experimented out, and the issue is always when you want to make experimental circuits, the wires are often very long, and in say many books about electronics you read, make the wires as short as possible, etc, etc. I've made another video about that issue, but anyway, of course, when you have at first an experimental circuit with all kinds of wires hanging out, the next step is to shorten that wires and make the components to be mounted as compact as possible. For instance, here this capacitor, it is say 100 nanofarad. Now it hangs here, but I'm surely gonna mount it here on that board with these brass pins. That's the way that I always make my circuits, with this brass pin, so that it is fixed and cannot move any longer. This wire is far too long, and of course I will surely shorten this wire to that potentiometer. And well, so that's say the most important thing when you make an electronic circuit, and you have, say, kind of haywire in that circuit. Don't hesitate to do these experiments. And that's the most important thing that I wanted to tell. Here, for instance, this is quite long. Perhaps I'm going to shorten this, make this wiring shorter. But of course, when you do experiments, you have long wires. You have, for instance, you must, for instance, test a capacitor, and in that case could be that you have here a wire, here to somewhere here, and also here, and that wire is quite long. But as long as we are talking about circuits that work in the, say, 10 kilohertz up to approximately, say, 10 megahertz range, you don't have to worry about long wiring. That was my idea, and I found that in practice, etc, etc. But of course, when everything works, the best idea is to shorten the wiring, to make the circuit compact. Anyway, let's see what this circuit can bring. This is only a vlog, by the way, where I wanted to talk about, say, experimental wiring and definite wiring. And this is the chip that I've showed in the first minutes of my video. Here it is. It sends out quite a good waveform. So again, don't worry too much about long wiring when you want to do experiments. Now I am on 77 kilohertz, and I want to say the circuit is not perfect. But anyway, let's see. Turn now the frequency potentiometer. You can see the waveform is completely pure. It changes to a lower frequency, 40 kilohertz, but there is now a certain jump when I turn the frequency potentiometer. That's also logical. You can use here a fine-tuning potentiometer, so an extra potentiometer to fine-tune in on the frequency. Anyway, I now want to show that jump in the frequency. Here I turn that frequency potentiometer very, very slowly. So here we have on the carbon layer of that potentiometer an enormous change in the frequency. You can cure it by using, say, another type of potentiometer or a parallel potentiometer for fine-tuning, etc., etc. Well, that's not the aim of this video. So, here we are with that chip, that beautiful chip, 40 kilohertz, beautiful square wave, and now I want to switch to the highest frequency that this chip can give. So let's see what happens. It's a beautiful chip, by the way. Of course, on higher frequencies the waveform, the square wave, gets more or less rounded. That's logical. It has in a certain way to do with the internal capacitances of the breadboard, with the capacitances, the internal stray capacitances of the wiring. But anyway, I want to focus not too much on that. So let's go to the highest frequency where it all can work. We can surely see that the square wave changes in a kind of sine wave. Has also everything to do with stray capacitance on the board. And now to the highest frequency, and it is 4 megahertz. The square wave is changed into a sine wave. That's in a certain way completely logical. Now I switch back to the lower frequency band. Let's see what happens there. Here we have a beautiful, beautiful square wave. I want to switch now back to the real, very, very lowest frequency band that this chip, this beautiful chip, can give. So that is 2 Hertz. 2 Hertz. And I want to publish the circuit as soon as possible. When it is completely elaborated, perhaps I have to make a multi-resistor amplifier, because the output of the chip in terms of voltage is not very high. The chip works on 5 volts, so the output can never be very high. So I turn the potentiometer back. This is really the lowest frequency, 1 Hertz. Anyway, now I directly switch to a very high frequency. And the circuit is not perfect. There are certain gaps in the frequency range, but anyway, thanks for watching. I'm on 15 minutes now approximately. And here again, that issue. Switch back. Again, thanks for watching. We are on 27 kilohertz. Well, I think that chip is very well usable for a good working square wave oscillator, and it is very cheap. It only costs approximately €1. I'm going to publish the definite circuit within, say, a few weeks. Thanks for watching.